This is Professor Kuehn, and today for our lecture we will be talking about submerged bodies or submerged objects. And the reference here is a student's guide, volume 2, chapter 15. This is from Pascal's Treatise on the Equilibrium of Fluids. The equilibrium of fluids. That's the reference. And just by way of background, to remind you that in chapter 14, Pascal had been talking about what we now call Pascal's principle. So let me remind you of Pascal's principle. The idea is that if we have a chamber that is full of fluid with a piston on one side, and we apply a force F1 to this piston, and the cross-sectional area of this piston is A1, then the idea is that this fluid-filled chamber acts like a force-multiplying machine. So there's an output force on this piston, F2, the area is A2, and Pascal's principle says that there's a specific relationship between these. Force 1 over A1 is equal to force 2 divided by A2. And this is just maybe to remind you that here we have this entire chamber full of fluid. Maybe I'll make this additional comment at this point. Pascal says in chapter 14 also that if this fluid were to freeze, so it's a solid, then you wouldn't have this force multiplication. It would no longer act like a force multiplying machine. So this is critically reliant on this being a fluid-filled system. Okay. Another way to think about this formula, by the way, is if you think about the force per unit area on this piston, you can call this the pressure that you're applying at position 1 is equal to the pressure that shows up at position 2. That is, any kind of pressure that you're applying to this fluid gets distributed evenly throughout the fluid and applies the same pressure on the other side. So you can think about it in terms of forces per unit area, or you can think about it in terms of pressure being applied in the fluid as being distributed uniformly throughout the fluid. Okay, so that is some of our background material. Now, here is what Pascal is interested in chapter 15. He's interested in the question of what happens to submerged bodies, and in particular, the interesting question is, how can we understand Archimedes' principle? Archimedes' principle. You might recall that back in the first few weeks of classes, Galileo was talking about falling objects, and he was talking about how when objects fall in a fluid, they're going to fall more slowly than when they fall in air. And there were two reasons for this. One was because the fluid exerts a drag force on it as it's falling. That's a fairly complicated phenomenon. The other reason is because the fluid exerts a buoyant force on this submerged on the submerged object. And how much the buoyant force, how big this buoyant force was, depends on the kind of fluid and the size of the object. And when we came across Archimedes' principle, we found that the buoyant force exerted on a submerged object, the buoyant force was equal to the weight of the fluid that is displaced by the submerged object. That is Archimedes' principle, that the buoyant force is equal to the weight of the displaced fluid. We didn't really explain why this is the case. All we said is there is a buoyant force, and that happens to be equal to the weight of the displaced fluid. Why is this? Well, we didn't know. What Pascal is going to do is he is going to give us a way to understand why Archimedes' principle is true. In other words, how can we understand Archimedes' principle? Not just what is Archimedes' principle, but why is it true? That's what Pascal is interested in. And let me just jump right away to the answer, and then I'll explain this in a little more detail. So here's the answer. And in order to understand this, you have to recognize that when you have a submerged object, so for submerged objects, the fluid in which it's submerged, the fluid exerts a force on every face of the submerged object. Okay, these forces, moreover, are not equal on every side. these forces are not equal on every side of the object. Okay, so what do I mean by that? So imagine we have, let me draw some water here. So we have water, and let's suppose that we put a block of material underwater. Okay, and the idea is that the water above it is exerting a downward force. Oh, let me do this a different color. So the water above this object is exerting a force downward. So that's the force acting on the top of this object. Moreover, the water on the side is exerting a force. So there's a force on the left side of the object. There's also a force acting on the right side of the object. And the fluid on the bottom is exerting a force on the bottom of the object. Okay, and the idea is that the forces on the left and on the right are going to be equal to one another. The force on the left is equal to the force on the right. So these are, in a sense, balancing each other right here. But, and here's the critical point, the force on the top of the object is going to be less than the force acting on the bottom of the object. In other words, this force right here is larger than this force right here. Now, that is critically important, that there's an unbalanced force on this object. So let me draw a line right here. So why is this important? So first we recognize that there's forces acting on every face, and now it's important to recognize that the difference, so the difference between the force pushing up from the bottom, and the force pushing down from the top, that is the difference between the force pushing up from the bottom and the force pushing down from the top, is the net force, or the total force, acting on the submerged object due to the fluid. Due to the fluid. And this is exactly what we mean by the buoyant force. That is the buoyant force. In other words, the buoyant force acting on this object is equal to the force, the buoyant force is equal to the force pushing up from the bottom minus the force pushing down from the top. The difference in those two forces is what we mean by the buoyant force. That is the net force acting on this object. And this buoyant force, we can show the buoyant force happens to be exactly equal to the weight of the displaced fluid. That is the fluid that is displaced by this submerged object. This might not be obvious right away, but we can prove this. And so that is what I would like to do now, is to prove that the buoyant force is equal to the weight of the displaced fluid. And by the buoyant force, I mean the difference between the force pushing up on the bottom and the force pushing down on the top. And I'm going to take a break for a moment and come back and explain this in a moment.